Hello and welcome back to our video series on inference. Thus far, we have looked at calculating and interpreting confidence intervals for proportions, for means when we have known population standard deviation, and for means when we have unknown population standard deviation. We've also looked at hypothesis tests for proportions, for means with unknown population standard deviation, and for means with known population standard deviation. In this video, we would like to introduce the idea of paired data. This is sometimes called before and after experiments. So, suppose we have continuous measurements which are measured before and after some treatment. Let's suppose, as an example, we have an exam on the material to be covered in the first day of class, and the grades are recorded. And then a similar exam is given at the end of the semester, and these grades are recorded. Now, notice that we have to have the same individuals on the first day taking the exam as we do on the last day taking the exam. So here we're going to have an exam 1, that's our before measurement, and then we're going to have our exam 2, that's our after measurement. Now, other examples where these are used might be in diet. Your before measurement would be your weight at the beginning, and your after measurement, the weight at the end. Pharmacological studies use these. Glasses and ecological impact. In these paired data, we have two lists of data on the same subjects. Hence the reason I said we need to have the same individuals taking the exam on the first day and the last day. So X sub BI, that's our before measurement on subject I, and then X sub AI, the after measurement on subject I. And notice, as an example, perhaps this is our data. Our before was 12, our after was 13, our before was 11, our after was 10. Our before was 10, our after was 12, and then our before was 11, our after was 13. In this paired type data, we're interested in the change. We're not interested in the raw data. So what we're looking at is the differences between these measurements. Now, depending on how you want to analyze the data, this difference could be after minus the before, or it could be the before minus the after. And so what this is going to give us is a single column of data. It's the column of our differences. Again, we're not interested in the raw data, just the differences. But what we would like to know is how to create confidence interval estimates or do hypothesis tests for these differences. As in our last video on t-distributions, we don't know the population standard deviation. We've only got a certain group. So we can't use our z-distribution. We need to use the t-distribution. Now recall the t-distribution relies on the number of degrees of freedom. We want to estimate both the mean and the standard deviation, right? Because we don't have the population standard deviation here. We've only got this sample. We do have n observations to use to estimate this mean, but the standard deviation, recall, relies on the mean, so the standard deviation has n minus 1 observations available for this estimation. So our estimates become d bar. And this is simply the mean difference. It's 1 over the number of differences times the sum of the differences. And d bar is the point estimate for the mean differences in our population. So d bar is approximately the mean difference, mu d. S sub d, that's going to be our standard deviation of the differences. And we're going to define this to be the square root of the sum of the d squareds minus the number of differences times the squared mean difference over the number of differences minus 1. Now, it can be shown that this is just a shortened version of our regular standard deviation formula. Our confidence interval for these paired data is then d bar plus or minus the margin of error, where the margin of error is our critical t star with its degrees of freedom equal to the number of differences minus 1, times the standard deviation of differences over the square root of the number of differences. And then our test statistic will be defined. It'll be d bar minus the mean difference in the null hypothesis, mu sub d0, divided by the standard deviation of the differences over the square root of the number of differences, and this is going to be distributed as a t with degrees of freedom equal to the number of differences minus 1. So let's take a look at an example of a confidence interval. Suppose we're interested in determining if Kaplan GRE prep works. And so we've got GRE test scores before Kaplan and then GRE test scores after Kaplan. And in particular, we'd like to create a 98% confidence estimate on the mean difference. And so what we have are our before scores and then our after scores. And then their differences. This DI is their differences. Now notice I took after minus before here. After minus before, after minus before, after minus before. And here I've got the squared differences. 2 squared is 4, 105 squared, 11,025. 88 squared, 7744. 16 squared, 256, etc., etc. And so our number of differences is 7. D bar is 1 over the number of differences times the sum of the differences. So if I add up the differences, I get 77. I divide by the number, which is 7, and I get a mean of 11. If I take the sum of the squared differences, that is 47,343, minus the number of differences, that's 7, times the squared mean, 11 squared, divided by 7 minus 1, and I take the square root of that, I get 88.03. Now I'd like 98% confidence, and so a T-star at 98% confidence with how many degrees of freedom? ND minus 1, that is 6. That is negative 3.143 and 3.143. And now I simply plug in my values that I have. My D bar was 11. My T star value was 3.143. Standard deviation of these differences, 88.03, divided by the square root of 7. And I get negative 93.57 to 115.57. And so we're 98% confident the mean score increase for Kaplan GRE students is between negative 93.57 and 115.57. So how might we do this in R? Well, let's take a look. Okay, so here I've got my before and my after. I've listed them, I've concatenated these, and I'll run these. Now my difference value, I've used after minus before. And what I've called diff val 2 is the squared differences. Remember, I need to square these for the standard deviation. And now, diff val 2 sum is just going to be the sum of these squared values. X bar diff I'll call the mean of my differences. X bar 2 is going to be the squared mean of those differences. Remember, n was 7. So if I look at the standard deviation of these differences, here I'm doing this the long way, the square root of the sum of the squared differences minus n times the squared mean of the differences divided by n minus 1. What do I get? Well, let's take a look. X bar diff, my mean difference, 11. My squared mean difference, 121. Standard deviation of these differences, doing this the long way, 88.0303. Now note, we could get the same thing if we simply did a standard deviation of the differences themselves, which I've called SD diff. And notice 88.0303. And so now I simply need to find my critical T value. I want 98% confidence, and so that means that I need 1% above, 1% below, and so I'm using QT of 0.99 with 6 degrees of freedom, 3.1426. Now I'm rounding that to 3.143. And my lower confidence value, X bar diff, minus my critical T times the standard deviation of differences over the square root of the sample size, negative 93.57. And then if I do the positive of that, and I just simply add the margin of error to X bar diff, I get 115.5749. And so we would say we were 98% confident that the mean difference in the improvement of these scores is in between negative 93.57 and 115.57. Now, that's the long way. But this could be done a whole lot easier if we simply use t-test. So, t.test. Notice I've got after minus before. I've got alternative equals 2.decided. Now, my mu is 0. I want to see if this difference is greater, if this difference is different from 0. Confidence level is 0.98. And notice this command I've put in, paired equals true. This is important. Paired equals true because we're dealing with paired data. And so if I run this, notice what I get. Negative 93.563 to 115.563. Negative 93.57, 115.57. Remember, we rounded our t value. And so there's a bit of rounding difference here. And so we could say that we are 98% confident that this mean difference is between negative 93.56 and 115.56. Okay, that's it for this video. In the next video, we will look at hypothesis tests using paired data. See you then.